Hello everyone, welcome to Computer Logic Design lecture number 12, and in this lecture we are going to talk about multiplexers and demultiplexers. So the outlines are multiplex and demultiplexer. At the beginning we are going to talk about multiplexer, after that we will be moving to the demultiplexers. So in very simple words, we can define a multiplexer circuit which has three different layers. So the input layer and the output layer, and there are some selectors or one selector that picks one input and takes it to the output. So the multiplexers have a number of data inputs. That when we refer to the data input, that means we've got some input lines, and each line can have a 0 or 1, and even it has one or more selected inputs. Select inputs, not selected, sorry, it's called selector, and it always has one output. So it passes the signal value, which is going to be 0 or 1, on one of its data input, which are those inputs, and pass it to the output through the selected signal. So the selected signal decides which input to go to the output. So here we've got a multiplexer. It has some data inputs, I0, I1, I2, I3, which can be 0 or 1, and it has one output. It always has one output, and it has two selectors. How do you know that? We've got four inputs. We can take the number of the inputs based on the number of the selectors we have. So the number of the inputs is 2 power 2 number of the selectors. We've got two selectors, 2 to power 2 is going to be 4. That means we've got 4 different data inputs. So how does it work? So the inputs, one of the inputs go to the output based on the selectors. So S0 and S1 and the output. So if S0, S1 is 0, 0, I0 goes to the output. So you can just convert those 0, 0 into decimal. 0, 0 in the decimal is going to be 0, so I0 goes to the output. So whatever I0 is, if it is 0, the output is going to be 0. If it is 1, the output is going to be 1. So if S0 is 1 and S1 is 0, that means 1 in decimal. Okay, so I1 goes to the output. So Y equals to the I1. That means whatever I1 is, the Y is going to be that data. So if S1 is 1 and S0 is 0, which is going to be 2, I2 goes to the output. If both of them are 1, that means 3 in decimal, and I3 goes to the output. That means Y is going to be the data put on the I3 input. And here we have only one selector. 2 to power 1 is going to be 2. That means we've got 2 inputs. And as we said before, the number of the output lines is always 1. So how does it work? Both of the inputs are connected to different AND gates. So you've got 4 inputs. That means we had 4 different AND gates, and all of the outputs are going to be connected to an OR gate. So the selectors are going to be connected to all the AND gates as well. The inputs and the selectors are going. So let's start from beginning and in a clear way. Each input is connected to an AND gate. That one as well. Each selector is going to be connected to all the AND gates, and all the AND gates output are going to be connected to an OR gate. This is how you can design a multiplexer internally. So if S is 0, that means I0 must go to the output. So it is 0, 0 comes here, this is going to be off because one line of the AND gate is off, and the 0 goes here, it's going to be 1. This side is 1, and I0 is whatever. For example, if it is 0, 0 goes here. If it is 1, 1 goes there. So this one goes there because this one is 0. 1 or 0 is going to be 1 at the output. That means if I0 is 1, the output is 1. If I0 is 0, the output is going to be 0. And let's take this example, which is we have 2 different selectors. 2 to power 2 is going to be 4. We've got 4 inputs, and always we have 1 output. So as we said before, each input is connected to an AND gate, as you can see that. But each selector must be connected to each AND gate. Okay, must be connected to all the AND gates. So, but how? We said that if S0 is 0, S1 is 0, I0 must go to the y to the output. So I0 is connected to that one. So S0 and S1 must be connected to that one, but they must be 1 in logic. So then y0 goes to the output of the AND gate, then it's going to be selected to the OR gate. So 0, 0 is going to be 1 and 1 here. If you can see, the output of the NOT gates are connected to the AND gate. So in this case, I0 goes to the output. But if you test, all of the other outputs are going to be 0. But if S0 is 1 and S1 is 0, this one must be activated, because this is going to be 1 in decimal and we need I1 to go to the out. So if S0 is 1, so this one is connected to the AND gate. But S1 is 0, that means this side must be connected to the AND gate in order to make the AND gate active and to pass this I1 to the output. But whenever S0 and S1 are 1, that means this one must be active. 1 and 1 are 1 and 1 to be converted to binary next to each other. Sorry, to be converted to the decimal when they are next to each other, that means 3. So I3 must be going to the output. So this one must be active. You can see this is 1 and the 1 connected to the AND gate. This is 1, the 1 connected to the AND gate. So in this way, the I3 is going to be connected to that one, and this one is already active because all 3 inputs are 1. So the output is going to be 1 and it goes to the through the OR gate, and the Y is going to be 1. Implementation using multiplexers. So sometimes we've been given a function like that one or a function like that one. So how to deal with that function while we want to implement them using multiplexers? Anytime you are going to be given a function with some parameters, okay, and some summation values. So how to extract those data there? So always take the last parameter as input and the remaining parameters as selectors. So in this case, we've got 2 selectors and 1 input, okay? 2 selectors, X, Y are selectors and Z as input. So, but all of them are input as well. So this is X, Y, Z, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 4 times 0, 4 times 1. This is how you can implement the multiplex, the truth table. So, and we can say that, as we said before, we've got 2 selectors, which are X, Y. And if you have 2 selectors, how many inputs do we have? 4. 2 to the power 2 is going to be 4, and we always have 1 output. So far, I think it's clear. And we can come to this summation. That means in which status we have 1 at the output. In state 1, 2, 6, 7. This is state 0. State 1, state 2, 3, 4, 5, 6, 7. So in state 1 and 2, 1 and 2, 6 and 7, 6 and 7, we have 1 at the output, if you can say that. So the output is F. So in this case, when the selectors are 0, 0, the input is 0, the data input is 0, and the output is 0. The input is 1, and the output is 1. That means F equals to Z, right? But in this case, 0, 1, X is 0, Y is 1. If the Z is 0, the F is 1. If the Z is 1, the Z is, if the Z is 1, the F is 0. That means the F is the complement of the input of the Z. But in this case, whenever the X is 1, Y is 0, in these 2 cases, which are the same, the Z is 0, the F is 0. The Z is 1, the F is 0. That means the F doesn't depend on the Z. It's always 0. Okay? And in this case, the F doesn't depend on the Z. It's always 1. So in those cases, when I0 goes to the output, this one, when they are 0, 0, I0 goes to the output, the input must be connected to Z. And I1 must be connected to Z complement. I2 must be directly connected to 0. I3 must be directly connected to 1. And this is the same example, but in this case, we have 3 selectors and 1 data input. So whenever we have 3 selectors, that means 2 to the power 3 is going to be 8. We have 8 input lines and we've got only 1 output. And in those cases, 1, 3, 4, 11, 12, 13, 14, 15, we've got 1 at the output. And in the remaining cases, we got 0 at the output, and we can derive those things based on the previous example as well. So that's it about the implementation. So in this example, we will learn how to make 8 to 1 multiplexer using the other multiplexers. For example, we have this multiplexer which is 4 to 1, and this is 4 to 1, and this is 2 to 1. So in this way, we can easily make 8 to 1 multiplexer. So we are going to get two different 4 to 1 multiplexers, this one and that one. So S0, S1, S0, S1. So if S0, S1 is 0, so that line is connected to that line, and that line is connected to that line. Okay? So if both of them are 0, in this case, I0 goes to the output, and in that case, I4 goes to the output. I0, I4 goes to the output, right? But what to do here? So we are going to depend on the S2. This is S2, okay? If it is 1, so that means 1, 0, 0, which is 4, I4 must go to the output. But if it is 1, I1 goes, so I4 comes here and it goes to the I1, I1 goes to the output. But if it is 0, that means in those two multiplexers, I0 came, I0 came, and if it is 0, I0 goes. So the one comes from this one gets to the output, because the one comes from that one is connected to the I1 and it's going to the output when this S, which is S2, is 1. So in case of 1, 1, 1, what goes to the output? 1, 1, 1, I7 must go, and let's check it. 1 and 1 here, I3 goes to the output. So you've got I3 here, and 1 and 1 here, this I7 goes to the output. So you've got I7 here. But what is the value of the S2? 1. So this one goes to the output, which is I7. Why? Because we took the I7 from this output and it's connected to that one, and this one is activated and it goes to the output. So that was all about the multiplexers, and let's move to the demultiplexer. So a demultiplexer is just opposite to the multiplexer. In the multiplexer, we have some inputs and only one output based on some selectors, but in the demultiplexer, we've got only one input and some outputs based on some selectors. So the number of the outputs is 2 to the power number of the selectors. So we've got Y0, Y1, Y2, Y3, which are the outputs, and we've got one input. So if both of them are 0, S0 and S1, the I goes to the I0. If 1, I go to the Y1. If 2, 1, 0, I goes to the Y2. If 1, 1, which is 3, I go to the Y3. And this is the internal design. It's just like the multiplexer. And that's all about the multiplexers and demultiplexers.